Video that illustrates the phase lines link that I shared on our Canvas page for this week. This is just another look at the logistic model with constant harvesting. In my Desmos video, you saw that I created sliders for those three parameters that were the growth rate, carrying capacity, and the constant harvesting rate. But when you click on this phase lines link, you're going to see that it's already preset to a state equation where it says y prime is equal to 1 minus y times y minus a. Now this is a logistic model. Here's the logistic portion right here that I'm circling around with my cursor. But the growth rate R and the carrying capacity K have both already been set to 1. So we're not going to be able to manipulate the growth rate and carrying capacity in this little demo. But we do still have the minus A here that represents the constant harvesting. So we're able to use the slider for A over here to see what effect harvesting would have. As we slide A together, we start to see the stable fixed point in green and the unstable fixed point in orange converge. Down here is the same graph that I was illustrating in Desmos. So this is a really nice link because it kind of gives you both perspectives where you're seeing the rate of change versus the state graph. These are the same. This is the same graph that you see in figures 3.7 and 3.8 on page 121. But you're also seeing the time graph up here. And remember in chapter 1 we talked about the two different types of graphs. There's like the state space graph. And for here, the state space would just be the one dimension y. And then there's the time series graph where you can see what happens to y as it evolves in time. So if we're applying this to ecology, we're going to kind of ignore the negative region here because negative populations don't make sense. We're going to focus our attention to the upper part here and pretend that this is some sort of population. If we start anywhere between 0 and 1, you're going to see the population always evolves towards the stable fixed point. If you start with a population that's greater than 1, likewise, you're going to go down in population until you eventually approach the carrying capacity. That's the stable fixed point illustrated with the green line. The fixed point at 0 is unstable, which means no matter how close I start to it, I'm going to veer away from it. And just to play with negative values for a minute, what would happen if I had a negative value is it would also be repelling. The 0 point is also repelling. So things go away from it below and then go away from it above. That's the difference between a stable fixed point, which are using green to denote, and an unstable fixed point, which they're denoting in orange. Okay, so now I want to show some more capacity of this link. And if you're also studying the book and you're looking on page 121 where you're matching things up with figures 3.7 and 3.8, go ahead and turn your attention to the previous page, page 120, where in figure 3.6, they show the phase portrait for the logistic growth. So in one dimension, because the one-dimensional state lies on a line, the phase portrait in one dimension is called the phase line. And so if you click on this, you're going to start to see the phase line. Now, different than on page 120, you're going to see that they're graphing the phase line as a vertical line as opposed to figure 3.6, which graphs it as a horizontal line. It actually makes more sense to graph the phase line vertically because that way you can see it directly match up with the actual time dynamics. So that's what's really fun about this applet is it's showing you the time series here, and then you can see how things match up with the phase line. And if you want to see how that matches up with the book, just think about rotating this to be horizontal instead of vertical. So now you can kind of see how time dynamics match up with things directionally pointing towards the stable equilibrium. So there's an instance where I started between the two equilibria. Here's an instance where I'm going to start above the equilibria, and you can see these dots illustrating the state still approaching the stable fixed point. And if I did start in negative territory, if that did make sense for what I was modeling, you would see that that trajectory veers away from the unstable fixed point. So that's all really cool. But really the most exciting and funnest thing about this is that it also provides us with a bifurcation diagram. We're going to be studying bifurcations in depth in section 3.6, but I thought I'd give you a peek ahead because I don't want you to be intimidated. bifurcation diagrams are actually the same thing in one dimension as this graph down here of y prime versus y. It looks very similar, except it's kind of rotated. So let's play with the slider for A and see what I mean by that. You can see that as I move the slider A larger and larger, and remember in ecology this kind of means that I'm harvesting from the population at a constant rate. Like I was saying in the other video on Desmos, you can see that the more you harvest, the closer the two equilibria start to get to each other, and they will eventually converge when you choose a harvesting rate that's equal to the height of the vertex of the parabola. You see them converge there, and then, oh no, no more fish. If you're harvesting too much, your model really predicts that there's going to be a serious downturn in the number of fish. Like, oh no, all my fish are getting eaten. I took too many. So remember, don't be too greedy with the fishing. You can harvest some, but you don't want to harvest too many. You want there to be a lot of wiggle room between the stable equilibrium here and the unstable equilibrium down there. So we already talked about how changing the parameter A causes a vertical translation in this graph down here. But now start to look at the bifurcation diagram. What a bifurcation diagram does is it plots just the equilibria as a function of the parameter. So here's the harvesting rate A as the horizontal axis on a bifurcation diagram. And on the vertical axis of a bifurcation diagram, we're plotting the locations of the fixed points. Okay, so let's set A to equal 0 so you can see what I mean by that. When A is equal to 0, you see that the two fixed points are 0 and 1. The orange one is at 0 and the green one is at 1. On a bifurcation diagram, when the value of A is 0, that means that we have an unstable fixed point down here and a stable fixed point right there. And as we increase the harvesting rate and we start to take more and more fish out of the population per unit time, you see that these two fixed points get closer together. You see them getting closer together down here, and likewise on the bifurcation diagram, you see them getting closer together as well. If you focus on the white line here on this bifurcation diagram, this white line here, that is corresponding exactly to what value of A I have chosen. And the really cool thing about bifurcation diagram is that when I focus my eyes on just one fixed value of A and I illustrate that on the bifurcation diagram as a vertical line, what is that vertical line? It's exactly the phase line for that chosen parameter value. So really, all a bifurcation diagram is, in this one-dimensional case, is it's taking all of these phase lines for different values of A, and it's lining them all up in a row to illustrate the location of the fixed points and the stability. We're using color to illustrate the stability of the two fixed points as a function of the parameter that we're changing. So this is just a sneak peek into bifurcations, but what is a bifurcation? It means a qualitative change in our situation. You see, when we're in this mode and we have these different harvesting rates, these two fixed points get closer together, but really when I'm trying to describe this as a big picture, there are two fixed points, right? For all these parameters of A that I'm kind of toggling around on here, I'm in similar situations, the similarity being that I always have two fixed points, one stable one in green and one unstable one in orange. But when I harvest too much, once I've harvested more than my population can handle, and you see now the state equation has dipped below, so the rate of change is always negative. If I harvest this many, I have no fixed points at all. And that's what we would call a qualitative change in behavior. It's a difference between having two fixed points, one stable, one unstable, and having no fixed points at all. And so the change that it makes as it goes from 2, converges just for a second to have one double root, and then disappears to have no roots at all. That's what we call a bifurcation. We're going to study those in detail more later, but it's always fun to have a quick look ahead.